Hello and welcome to Intermediate Algebra, Unit 8, Lesson 1, where we will look at square roots and higher roots like cube roots. Our lesson objectives are so that after you're done with this lesson, you should be able to evaluate a square root. In other words, simplify it. The square root of 4 is 2. Use the product rule to simplify square roots. You can, knowing how to break them up and using the product rule, using the quotient rule to simplify square roots, and how to evaluate and simplify higher roots, third roots, fourth roots, fifth roots, and general understanding of what a root means and what the index means. So, I think you are all a little bit familiar with square roots. So the square root of 9 is 3, because 3 times 3 is 9. Okay, we remember that. And you say, well, what's the square root of 10 have a root? Well, it doesn't have a simple integer square root, but it does. But the square root of 16 is 4. But why don't we say it's negative 4? Because negative 4 squared is also 16. The reason we don't say the square root of 16 is negative 4 is because when you're asked to find the square root of a number, it's an arithmetic problem, and arithmetic problems have one solution. So if you were asked to find all of the values of x that made this equation, x squared equals 16, true, there would be two solutions, because you're not being asked what's the square root of 16. You're being asked what number or numbers multiplied by itself will give you 16. It's just a little bit different than being asked for the square root of a number. It's an algebra problem, not an arithmetic problem, and you can have more than one answer to an algebra problem, an equation. So a lot of times this is a big mistake students make in solving quadratic equations, which we'll see in the next lesson, is they forget that, oh, there's two answers because I'm not just being asked for the square root of 16, I'm being asked for all numbers that can replace x and make this true. It's a very important point. Though it might be a little too subtle for you now, when you get into the solving quadratic equations, you're going to have to be very cognizant of this. So algebraic equations can have more than one solution. That's the bottom line. But our arithmetic calculations only have one solution. So, and we go back to this idea of the principal value. That's saying that, hey, this is square root of 16 is an arithmetic problem, so the principal value is always used. It is 4. The square root of 25 has a principal value of 5. Now, if I put a negative sign in front of the square root, this really becomes a multiple step evaluation. Radical symbols act like parentheses. They are grouping symbols. We kind of overlook that. So what you do, what's inside there first. So the square root of 16 is 4. Then you put the negative on it. So that is a way you would get a negative when a problem involved the square root of a number, but it would have to be out here. And the same thing for negative of the square root of 25. Well, the square root of 25 was 5, so its opposite is negative 5. So here are some more examples. We're going to evaluate square root of 49, square root of negative of the square root of 64. And what do you do when you have a radical? It's a fraction or a sum. There's no letter D there, but that's the fourth example. You can't do these individually, but you can do these individually because it's division. We'll see that. So for A, the square root of 49 is 7, because 7 times 7 is 49. Your calculator probably has a button for square root, and if you put square root of 49, you'll get 7. You should know your perfect squares. I will make a table of perfect squares and perfect cubes available to you on our website, and if you don't know them, you use that for reference as you do your homework, but really try to learn them. So B is one of those two-step problems. First, I take the square root of 64 because the radical is a grouping symbol, and then I take the negative of that. I get negative 8. And we'll see the quotient property of radicals allows us to take the square root of 1 and the square root of 25 individually and make that ratio the answer. So the square root of 1 is 1, the square root of 25 is 5. So I get 1/5. And indeed, if you multiply 1/5 times 1/5, when you multiply fractions as top times top, bottom times bottom, you get 1/25. Now, it's tempting to say, oh, this answer will be 7 because I'll do the square root of 9 plus the square root of 16. You cannot split up addition and subtraction within a square root. Because that radical is a grouping symbol, you do what's inside first, which gives you 9 plus 16 is 25. Then you do the operation, that is taking the square root. So you do whatever's inside first. In the case of the 64, there was nothing to do. That was already simplified. But 9 plus 16 becomes 25. Then you take the square root and get 5. Now that problem is different than this problem where the square roots are broken up in the original problem. There's nothing to simplify here with the 9, so you get a 3. There's nothing to simplify with the 16, so you get a 4. So you do each of those operations first and then you add. So be careful of your order of operations. Realize a radical symbol is a grouping symbol. So you try these. Stop the video. Try each of these, and they're very similar to what you just did, and then we'll see the answers when you come back. All right, you're back. I have no way to know, but I will believe that you stopped and tried these. So here are the answers. Square root of 100 is 10. That's pretty straightforward. Now the square root of 4 is 2, but there's a negative sign in front of the radicals, so you get -2. Square root of 1 is 1, square root of 16 is 4, 1/4 times 1/4 is 1/16. That works. You have to, for D, you add the two things together and get 100, then take the square root and you get 10. But in E, the order of operations is different because the addition is not inside the radical with the numbers. So you get the square root of 64 is 8, the square root of 36 is 6, and when you add them, you get 14. Hopefully that is clear to you. If not, we need to get you some more practice. So, another important point to remember is that if you take the square root of a number that's a perfect square, you really, if it's not a number, it's a variable that's a perfect square. Sorry, so you know some number A, you're taking the square root, you really get the absolute value. Because if you take the square root of the number 3 squared, you get 3, because 3 squared is 9. And oh look, -3 squared would also be 9, so you'll get 3. And you'll lose the fact that the original problem had a negative in it. This only becomes a detail when you're solving equations. The square root of x squared, we kind of throw it around and just say, oh, it's x. It's actually the absolute value of x, which is why you get two answers for x squared equals 16, because you get the absolute value of x equals 4, and there are two numbers whose absolute value is 4. 4 and -4 have the same absolute value. So here's the product rule. We can't break up sums, and we can't combine the square root of 16 plus the square root of 9, but it turns out we can combine products. So I see square root of 16 is 4, square root of 9 is 3, and when I multiply them I get 12. Well, it turns out 16 times 9 is 144, and the square root of 144 is 12. That works every time. So written as a rule, I can either separate inside a radical by factoring. I factor my number, I factor my 144 into 16 times 9, or I can take two square roots that are multiplied together, not added or subtracted, and make it the square root of the two, what we call the radicands. The item inside is the radicand, what you're taking the radical of. I can multiply A times B and then take the square root. The order is kind of commutative in a way. So a square root is simplified when the radicand, the 144, or here the 16, has no perfect square factors other than 1. So we use this product rule to factor our radicand into a perfect square times something else, and then we can take the square root of the perfect square. For example, I have been asked to take the square root of 150. I've been asked to simplify it. Now, you can punch this in your calculator and get a decimal answer, but when you want answers in exact form, and in my math lab and your homework, a lot of these, they want exact form. When you're asked to simplify a square root, we're not looking for the decimal estimation of it, because it is only an estimate. We're looking for a simpler way to write it, maybe still using a radical. So 150, you can divide 150 by 25 and get an integer. 25 times 6 is 150. So again, it's helpful to know your perfect squares. I would start by dividing 150 by 4, then 150 by 9, because that's 3 squared. Then I'd try 150 divided by 16. That didn't give me an integer factor, but when I do 100, the next perfect square is 25. 150 divided by 25 gave me 6, so I'm going to rewrite the 150 as 25 times 6. Then the product rule allows me to evaluate the square root of 25 and get 5 and keep that multiplied by the square root of 6. 6 has no factors that are perfect squares, so this radical is now simplified. So here's some more examples of using the square root property. Square root of 300. Well, perfect squares. 100 is a perfect square. Whoops, sorry, I didn't mean to go that forward. There we go. 100 is a perfect square. So 100 times 3 is 300. I get the square root of 100 is 10. And the square root of 3 is as simple as it gets, so it's 10 square roots of 3. It's like the radical has a coefficient of 10 now. Now that's using the square root property to break up the radicand. Here we're going to simplify this by making a single radicand and seeing if there are any perfect squares in it. So I take the 4x and multiply it by the 2x and I get 8x squared. Well, 8 can be written as 4 times 2. So I get the square root of 4, and x squared is a perfect square, so I get the square root of x squared times the square root of 2. So this says 2x square roots of 2. The truth is it's really 2 absolute value of x square roots of 2. I won't be really fussy on that, but I want to be consistent with what we talked about in the last slide. Now the reason we don't write it here is because both 4x and 2x can't be negative numbers. You can't take the square root of a negative number in the real number system. So we know that x is really just a positive value, so that's why it's okay just to leave it without the absolute value. That is a detail. It won't be of importance as far as getting points on tests, but it is something you may see later. So again, there's 2 examples for you to try. One where you use the product rule to break up the radicand, and one where you multiply to make a bigger radicand that may contain perfect squares. Stop the video and try these and come back and we'll go over the answers. Okay, you're back. Let's see how we did. So the square root of 48, I divide by 4, and it didn't work, and well, it did. I got 4 times 12, but then I'm going to have to break up the 12 again. That may not be the biggest perfect square, so you want to look for the biggest perfect square. So 4 works, so the next thing, I try 9, it doesn't work. I try 16. Oh, 16 times 3 is 48. That is the biggest perfect square because 3 contains no perfect squares. So I break that up into the square root of 16 times the square root of 3. The square root of 16 gives me 4, and the square root of 3 is as simple as it gets. For B, I get to multiply the 6 times the 12 to get 72, and an x times x gives me an x squared. So I get the square root of 72 times the square root of x squared. Square root of x squared is just going to give me x for the same reasons as we saw in the previous example, part B. 72, I divide by perfect squares and I see that 36 is the biggest perfect square that goes into it. So the square root of 36 gives me the 6. I still have a 2 inside the radical, and then I have the x, but we don't usually write it in this order because it can be confusing. You don't necessarily know where that radical bar ends. So if the x is not inside the radical, we write it out in front kind of as a coefficient. Okay, now the quotient rule is really similar to the product rule. As long as you're not adding or subtracting, you can combine or split up using multiplication and division. So here we just tell you b isn't 0 because you can't divide by 0. So for any problem where this is valid, so where b isn't 0, this quotient rule works that you can divide up a fraction that's under a radical into the numerator under the radical and the denominator under the radical, or if the radicals have what we call the same index, these are both square roots, there's an understood 2 there, then we can combine into a single radical. The indexes do have to be the same. So here is a square root of a fraction. I can break it up into the square root of the numerator. So I had the square root of 81 over 4. I can find the square root of 81 and find the square root of 4 and make a ratio of those two, and that will be the correct answer. If I multiply 9 halves times 9 halves, I get 81 fourths. Now part B uses the reverse process in the rule where I have a square root over a square root. So I'm going to take the numerator and denominator and see if I can simplify that, then take the square root. So 75x squared over 3x, 75 divided by 3 is 25. X squared divided by x leaves me with an x. Square root of 25 is 5. I can't do anything with the square root of x because it's only got a power of 1. It would need a power of 2 or more for me to simplify anything. So you try these. They're similar using the quotient rule. Stop the video, come back, and we'll go over the answers. Okay, you're back. Here we go. So the square root of 16 over 25, the square root of 16 is 4, the square root of 25 is 5, the answer is 4/5. For the square root of 150x cubed over the square root of 2x, the 150x cubed over 2x becomes 75x squared. 75 can be written as the perfect square 25 times 3. The x squared is x squared. So when I take the square root of x squared, I get the x, and they all had to be positive here, so I don't have to worry about the absolute value because these were odd exponents in the beginning. But again, that's a detail. And I take the square root of 25 and get 5. The 3 stays in the radical. I typically put the x out in front because it's confusing as to where the radical ends otherwise. All right, so that's how things work with square roots. Well, those same rules work for what we call a cube root or a fourth root or any higher root. For square roots, see that little n there? This template means there's a number there. For square roots, there's nothing there. It's assumed to be a 2. When that, what we call the index, the n, is missing, it's assumed to be a 2. A lot of times in mathematics, things that are missing, like if I just say x, that means the coefficient of x is 1. We either assume it's a 1 or a 0, but in this case, a missing index is a 2. But that index can be a 3 or a 4, or really any positive number, 2 or bigger. So the square root of the nth root of a equals b means that if I take b and write it down n times and multiply, I will get a. So the cube root of 64 is 4 because 4 times 4 times 4, the 4 cubed, is 64. The fifth root of 32 is 2 because 2 times 2 times 2 times 2 times 2, or 2 to the fifth, equals 32. In the cube root of 64, the index is 3, the radicand is 64. And the fifth root of 32, the index is 5, the radicand is 32. So if the number inside, if A is positive or 0 and B is positive or 0, if n is odd, A and B can be any real number. You can take the cube root of a negative number is basically what this is trying to say. The square root, the cube root of negative 8 would be negative 2 because three negatives multiplied together give you a negative. The reason this doesn't work with square roots is you'd be writing down two numbers and multiplying them to get the radicand, and a negative times a negative will give you a positive, and a positive times a positive will give you a positive. There's no way to get a negative number if the index is even. But if the index is odd, you can indeed get a negative number. If the index is even, you cannot. So the fifth root of negative 32 is 2, but the fifth root of negative 32 is negative 2, but the fourth root of negative 16 doesn't exist because this index is an even number. And if I write four negative numbers down, if I write negative 2 down 4 times and multiply, I end up with a positive number because there are pairs of negatives multiplied together. So here's some examples with higher roots. The cube root of 40. You can still simplify. Now this time, instead of looking to take out perfect squares, you're looking to take out perfect cubes. So you skip the 1 usually, but 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. So you would divide by those numbers to see. So the 40 divides by 8. So I get the cube root of 8 times 5. Cube root of 8 is 2. Cube root of 5 contains no perfect cubes. I'm done. This one uses the product rule in the opposite order. Fifth root of 8 times the fifth root of 8. Now, fifth root of 8 doesn't have any simplification, but if I combine them, it might. So 8 times 8 is 64. Now, fifth roots are trickier. Always look for the 32. 2 to the fifth, this 32 shows up over and over again. But 64 is 32 times 2. So fifth root of 32 is 2. Fifth root of 2 is 2. We won't be doing too much with higher roots. If you go into some computer coding classes and things, you do see a lot of powers of 2. But mostly cube roots you'll see in this course, but you need to understand the meaning of a fifth root or a fourth root or a seventh root, not just a square root. For part C, problem C, cube root of 125 over 27. Let's break this up using the quotient rule. Cube root of 125 is 5, and you can find that in your calculator. There's usually a button. We'll see how to do that with exponents in another lesson here. Cube root of 27 is 3, so you get 5/3. So you try these. They're similar in the pattern. You've got problem A, problem B isn't noted here, and problem C. They're 3 separate problems. Stop the video and try these. All right, you're back. Here are our solutions. 24 has a perfect cube of 8 in it, so you get 2 cube roots of 3. For the second problem, you're going to multiply, you get a 32. Well, 16 is 2 to the 4th, and so you can take that out. You get 2 to the 4th root of 2 can't be simplified. And when you do the 4th root of 81, you get it 3, and the 4th root of 16, you get it 2. Dividing this ahead of time didn't actually help you. You just do them individually. All right, so that's the end of this lesson. Now you have some homework to do, and if you have any questions, you should email me, get some tutoring help, and thank you for joining me.